So in this quiz, the lab quiz, you will see some information that I provided and some question they have to answer. Like this one here, simply just provide the information. You watch this video to get an idea about the unit cell and how we count as a unit cell and how the crystal structure looks like and their property. So you watch this by yourself. Then you move on to the next one. It's going to see some text information that we kind of briefly talk about 4 different basic crystal structure. You have more kind of a crystal structure than these 4 kind of simple things. As a matter of fact, there's no such like a simple circuit elements, I think. But it's just give us idea how we can characterize the property of a qubit system. So we will put an emphasis on the 3, but we use the simple qubit as an example. So when you see this instruction, we simply just look at the simple circuit, simple qubit, then you work on the rest of the 3. This picture over here actually is in the slide of your lecture, okay? And I give you the definition of the APF, okay? So APF, atomic packing factor, meaning how small, it's very like the density, but we're looking at the ratio of the volume. And it's the ratio of the volume of the unit cell and the volume of the atoms. So you have several atoms inside of this unit cell, and we wanted to see what percentage. Okay, can you guys see the screen now?
It's frozen for me.
Yeah, it
frozen
from the. It still says like published courses.
It doesn't show, or but can you guys hear me?
Yeah.
Yes.
Okay. If you can hear me, that should be fine. I mean, all I do is, and you can open your course canvas as well. I'm just simply just kind of tell you what you have to do. So if you open the canvas and you be able to click on the Lab2 lab, which is a quiz, and I simply just go through the quiz very quick. Just tell you what you have to do. Okay, so I hope that you can see my screen because I'm simply just, I'm on still on the second one, which is providing the information to define how you can find the APF. Okay, this is a part of your coming exam, so make sure that you understand the material of this lab. So the APF definition is the volume of the atom in the unit cell, meaning how much of the volume occupied by the atoms, and divided by the volume of the unit cell, which is a cubic. To find the volume of a cubic, that means you need to find the lattice constant, which is actually the length of a unit cell. So a cubic has 3 dimensions, but each one of them are the same. So once you find the H length or the lattice constant, and that is that will give you the volume of the unit cell. A more complicated is how do you find the volume of the atoms in the unit cell? Then this depends on the radius of the atom. It also depends on how many atoms that you have inside of this unit cell. And that's why you need to calculate, you need to figure out what is the coordination number. You need to find out the number of atoms inside of this unit cell. And then you need to find out the radius of the unit cell as well. And then you can just watch those information. And I do give you the example how you find the simple cubic. Again, as As a matter of fact, there's no elements actually is the simple cubic. Once you read through that, the next one is that you also need to identify, if you have a cube like a unit cell, where you're going to have the most dense edge and where you're going to have the most dense plane. So the most dense edge or the most dense direction and the most dense plane, it's going to relate it to your chapter 4. I know you just start with the chapter 4. What does the chapter 4 talk about? Have you guys watched the video yet? Okay, let me give you a general idea about the first part of this material course is going to talk about. Why do we use material? We use material because the material has some kind of property. And most important property about the material is the strength. And where is the strength of the material coming from? It's coming from atomic bonding. So if you have different kind of bonding and each one of bonding give you different kind of strengths, and depends on what kind of material that we're using, and you try to use the advantage of the strengths of the bond. Now, if the material fails, simply just mean the bond break, and what would be the situation the atomic bond will break? If you provide a large force, or another way is that you provide with, you are sustaining with a large load, you're going to break the material. And then you look at the unit cell. Unit cell is the smallest elements of this atom. If the material has more packed direction, that means the atom is lined up so close, normally the bond is going to be stronger. So we are interested about which direction you're going to have the strongest bond, and what plane, because it's a three-dimensional, and what plane that you're going to have the most dense plane that might cause the loading to be stronger. You can also think about the other way. If the plane of this unit cell is less dense, it's more like loose, then it's likely it's going to break in that direction. So that's why we wanted to also understand in this crystal structure, which direction you're going to have most dense plane or most dense direction. When we talk about direction, we're looking at a line, like just like X and Y and Z axis, things like that. But it doesn't have to be just going along the X or Y or Z. You can go diagonal, right? So you guys haven't started the Miller's indexes, right? If you guys going to start with that topics, that will be our probably our next lab. So that is also related to the topic of this, like where is the direction you're gonna have the most dense direction, and where is going to be the least dense direction, and that is part of this study of the material. Okay. So this one is a multiple choice question, and I mark A, B, C, and D, 4 different plane, and you need to find out in this simple cubic, okay, simple cubic. And if you go back to the simple cubic, this is a single, like a simple cubic. Which direction, which plane you're gonna have the most dense material? So one of the plane is this plane, which is simply like you cut it through with a diagonal. And you look, you you kind of use your imagination. How many atoms is actually project to that plane?
Professor, we cannot
Yes.
see your share screen.
You cannot see my share screen?
Yes.
Okay, let me try to reopen my share screen again. Can you guys see it now?
Yes, yes.
Yeah.
Yeah.
Okay. Sorry. All right, so I'm talking about this question that you're going to do, which is the first question you have to answer. So symbol cubic, you have 4 on the top, 4 at the bottom. They all line up. And this is what we call a reduced sphere model. The actual model should be like this. Okay, and you look at this one. This face over here is the same face as this one, is the same face on the top. So 6 faces, they are all the same. Are they the most dense face? When we say the most dense plane, meaning how many atoms project on this square. So you can see, I'm just using this plane as an example here. Let me use the annotation. If I just use this plane as an example, this is like a quarter of the atom. You have 4 quarters of the atom. That simply just represent like a 1 whole atom will occupy this plane. So you can calculate the density of this plane occupied by the elements. This is the most dense one? It probably is not. And if you look at some other options, one of the options is you can go diagonal like this. Right? If you go diagonal like this, and you can also try to figure out how many atoms actually project on this plane. The area of this one is different from the area on but it might also have more of the atom project on this plane. So you have to figure out what is the area of this plane and how many atoms project on this plane. And then you can find the density of the area was occupied by those atoms. So what I was trying to say before is that if this plane is more dense than this diagonal plane, then if you apply a load to an element, it's more likely the element will break along the diagonal if the diagonal is less dense. If this one is more dense, it will be harder for it to break in that direction. So that's one of the things that we wanted to understand, which plane that you're going to have more dense. Any question about this part? So this is a multiple choice question. You choose one, which is
Professor,
yes.
on that kind of unrelated a note, I'm getting some emails of some people that are in the class too that they can't access this, I guess, because they don't know about pressing the Lab2 picture. I don't know if you want to mind sending an inbox to everyone. Maybe that's why we're missing some classmates today.
I just sent out an email. I just let's see. Seven 77288. Am I using this one? Let me check. Yeah, 996-772-AA. Hey, did you have trouble again? I can't hear you.
So yeah, the link that you shared in the email is not correct. I think what you have,
Oh,
yeah. So I was texting.
pressing the icon?
Yeah, so I think the correct icon is the one you sent it actually is help me out with it. It's the one that is if you go into Canvas,
Okay.
it's on the let me see if I can't share my screen. Maybe I could send you a screenshot.
Okay, I will resend the email. I'm just kind of curious why I'm missing so many people here today.
Yeah, I was freaking out too.
All right, well, we actually record this one, so
Okay.
you didn't miss a lot. Let me resend this one here.
Professor, did we go over the graph portion already?
No, not yet. I'll go over later. So pronto. Okay. Okay. Come back. Okay, if you just get into the to this room, just click on the week 3 Friday, and I'm looking at this one here, the lab 3 here. Okay, I just finished the first part and simply just tells you there's information that given to you when you start this lab, and then after the information, I will ask you to do something, and then you have to either choose the right answer, enter the right answer, or you're going to submit a file. Most of them, you're going to submit a file to show your work. So you can take a picture of your work, and then you submit how you get those answers, and then you're fine. So this one, I just show that you use the simple cubic as an example to understand the idea for each one of the calculation. Then the most of the work that you can start with is actually the question 2 over here. When you get into this, who just come in? Okay, sorry if you couldn't get in before. We just started, and this is a recorded. So these are the things that you have to do. The 6 points over here. You can follow this order to find the answer. So try to find a coordination number, meaning how many atoms connect with this center one, right? This one probably is very obvious. You can see how many atoms actually touch with this one here. And how many atoms in each one of the unit cell. This is a 1 unit cell. This is more like a realistic, more like a proportional to the size of the atom. This one is what we call the reduced sphere unit cell. Okay. The first few part, you use this one here which is easier to understand. You can see the coordination number for this case should be 8 because you touch with 4 on the top, 4 at the bottom. You don't touch with the sides. There's nothing here, nothing here, nothing like just in the center of the face. So it's only on the edge. So there's like a coordination number. And the second one here is how many atoms that you can count it, right? Each one of them is how many of the portion of the atom that you count, then you can find out how many of the atom inside of the unit cell. The volume of the atom depends on how many the atom that you have. Okay, so you have to write it in terms of the atomic radius. So what is the atomic radius? We don't know in this case, but if you know the ratio, then you can find out later. So this will be the radius of the atom here. And let's see, what else? So you find those things, then you can find the APF where we defined previously. It's just the ratio of the volume of the unit cell and the volume of the atom inside of the inside of the unit cell. So you can find the ratio, which is the APF. The last one here, the number 6, then you have to use this one to show where is the most packed direction and where is the most packed plane. Okay, so for example, if you want to say this is probably one possibility and this one is going to be the same as the horizontal one, so we are not going to look at, if you think this is the one, then you don't need to show, like this direction is going to be the one as well. The possibility that you might have to be the most dense direction might be this direction, or this direction, or this direction. They all represent different direction. So you need to point out which direction will give you the most dense direction. When we say most dense direction, meaning along this line here, do you have most of the line occupied by the atom? If you look at this line here, and you compare 1 and 2, which one is more dense? I think this is very obvious. This one is more dense, right? The whole line is occupied by this atom over here, but actually it's not. If you look at this direction, this shows more accurate picture of what that is. It's not fully occupied. It still has some space over here, right? But then you compare from this one, so I should draw at here. I should draw at here. It's obvious this one is more dense than this one. But do you have any other direction will be even more dense?
Yes, from the corner across the cube.
Yeah, if you go this one here, if you go diagonal, this one is more dense. Okay, so that's what we mean the close packed direction. Now, once you see this one is more dense, then you draw the line and point out that one is the most dense direction. So then this one will be the most dense direction. The second one is the packed plane. So you look at the plane. So the plane will be similar to the simple question that you answered previously. So you have to look at which plane that will give you the most dense plane. Okay, any question about this one?
Just to confirm, direction is just a straight line and then plane is a plane.
Yeah, the plane is the plane. So if you look at the plane, you'll be like say, you know, this plane. Or this plane. Or let's see here. This plane. Okay, you could also have a plane go this way. Right. So if you learn like a Miller's index, and they will tell you, you know, some of the plane are the same. Like if you look at the plane of this one here, this face over here, and the plane on the back, they are the same. The arrangement is the same. There's no difference. The plane on the side over here is the same plane on the top. So we call this like a plane family. They are the same plane. Doesn't make any difference. But some of the plane are different. So the plane I draw is going to be different. The plane in the middle is different from the plane on the edge. These two are different. Okay, so they're not necessary to be the same, but depends on where you look at that. And then we have a way to identify different plane. How do you actually mark these two different plane? And that's what we call the Miller's index. So you're gonna learn this one. I'm not sure you guys started or not. So this is another important topic that you're gonna learn. Okay, any other question about this one here? And then we're going to look at the following things. So you do this one for the BCC, and you're also going to do one for the FCC. So the second one is the FCC. You follow the same procedure and doing the same thing and try to find that, and you just upload a file. Unfortunately, this kind of design only allow you to upload one file in one question. So try to put it all in one page and just take one picture and use that file and submit it over here. If you cannot make it just one page, what I would suggest that you can copy those image to a Word documents, and you submit that Word documents, that will work as well. Okay, so if you cannot make it into one image, then you might want to open the Word documents and put that all into Word documents and submit that one. So you can only submit one file per question. Any question about this part? All right, let's look at the last one. The last one probably is the most challenging one, because FCC and BCC is easy to understand. The last one, we're going to look at the HCP. HCP is more like a hexagon, and so if you look at the unit cell, this one here is not a unit cell. Okay, this one here is actually 3 unit cell of the HCP. If you take part of this, which is this one here, and we just enlarge it to the right, and this is the unit cell. But to visualize what the HCP looks like, we draw this hexagonal to understand how they are arranged. So there's another one over here, and there's another one over here. So you actually have like three of them. But we cut it through, then we can see just one of them, and this is one of them. This one gives you a more clear picture how they arranged. And I give you the instruction how they arrange. When you solve this one here, you're looking at this unit cell. How do you find the volume of the unit cell of this shape? It will be simply the area at the bottom times the height. Okay, so how do you find the area of the bottom? This is not like a
3 square times C.
It's a 1/2 of this space times the height of this. Is the parallelogram. It's not like a square, right? So that one you have to calculate what this parallelogram is. And then you need to know the height. And the height, in order to know the height, you have to figure out a ratio between the height and the A. So this is a challenge to find. If you can find, the answer for that is 1.633. And I give you an instruction how you can find that. So if you follow through this instruction, and you will be able to find as a C over A, and which will be 1.633. And then you can find the coordination number, volume of the atom in the cell, and also the rest of them, and you can find the solution. Okay, any question about this? Hey, John, sorry, I didn't know the link that I sent was wrong. But this one is also recorded, so I will put this video on Canvas after this. Any question about this part? This is the last one that you have to do. Okay, any question about the lab? This lab is due by the end of the day. You have to walk through all this calculation and also make a copy of your work and submit that. And I do recommend that you try to do this by yourself, but you can discuss with your peers if you have questions, and you guys can share how you look at the things, because this is three-dimensional. Some of the thing is harder to picture that. So so it will be probably the better that you can look at this kind of three-dimensional things, that you can visualize how it was arranged. And this is going to help you on your exam as well. So that's why I wanted to emphasize this part here. Any questions about this lab? If not, then you can work on your own. I'm not sure you guys wanted to use the breakout room. I guess you guys can open your own room if you wanted to. Then you can use the Zoom to open the room and discuss with each other, or you have some other way you want to discuss with your peer, you can do that. I will end the recording at here for this lab. Then I am going to answer some of the questions that you guys have for the lab 2. I know that a lot of people ask questions about the lab 2. So I'm going to stop the recording right now. Okay,